Okay, thank you, Aldo, and thanks for coming. So it is my great honor and pleasure today to talk to you about the important role of optimization and statistics in the modern data science, the challenges it faces. You mean this one? So is it okay? Okay, maybe I should stand here, maybe. So talk to you about the important role of optimization and the statistics in data science, the challenges it faces, and how we overcome them. So we have all heard of many exciting technology achievements in recent years. Computers can detect different objects, recognize and translate spoken language into text. And we can also do many fancy stuff like self-driving cars or like the computer playing the game Go. Researchers are also working hard to provide medical treatment and products tailored to the individual background of the patients. And engineers are planning power systems to accommodate the need of the gross energy, particularly because there are some uncertain production of this kind of renewable energy. So data science is a new kind of science, and actually optimization and statistics play an important role behind all these applications. So here is the overview of my talk. It has 3 parts. In the first part, I will talk about the mathematical formulation of data science problems and provide some intuitions about the challenges it brings to the field of optimization and statistics. And in the second part, I will talk about the computational method and the statistical analysis to solve a class of optimization problems behind these applications. And in the last part, I will talk about the extensions of our approach and also my concluding. So what is data science? On a very high level, we say that data science is about learning patterns in data. So let's say a simple example. Suppose these are the empirical data that we can observe in practice. The horizontal coordinate represents the input, and the vertical coordinate represents the output. So we are trying to extract the information behind this data, understand and learn the patterns of this data, such that in the future, when there comes a new input, we can predict the position of its output. Or more formally speaking, data science is about finding suitable functions, or we call models, given examples of desired input and output behavior. So we have some training data. And what we are trying to do is to find a function or a model f sub theta. Theta is the training parameter, such that the averaged inconsistency between the model's observed output and the observed output is minimized. But of course, you can use many more general loss functions. But here, for simplicity, we just use the square laws to illustrate what we want to do. And for most of the time, we need to specify the functional class, the capital F here, within which we want to fit the model or the data. Because otherwise, if we are given too much freedom, we can almost always draw a curve, very complicated curve or surface to pass across all the data. But this will, on one hand, make the model or the function too complicated to estimate and interpret. But on the other hand, it may also overfit the data, such that it cannot generalize well for the future instances. So for example, perhaps the simplest functional class is linear functions. Now what is this problem about? So it reduces the classical statistical estimation problem, where people call the linear regression, meaning that we believe there is a linear relationship between the input and the output data. And the right figure illustrates what the result of the linear regression when we use it to fit the empirical data. But actually, we can consider some nonlinear functions. For example, we can consider the so-called max functions, where there are 2 pieces. One piece is fixed to be 0, and the other piece is a linear function to be estimated from the data. So this class of functions look quite simple, right? But actually, it plays a very important role in the modern data science. I'm sure that people here are all heard of the deep neural network, a mathematical model in deep learning. And actually, this kind of function is a building block for a particular kind of deep neural network. And I will talk more about this application later in my talk. So what about some more general functional class? We want to make the model out of function. We want to give more flexibility of the model. So can we talk about the continuous piecewise linear functions? Can we fit the data within these continuous piecewise linear functions? And actually, you can observe from the figure that within this class of functions, we can almost exactly recover the underlying patterns behind this data. And actually, the majority of my talk is about in a very high-dimensional space. How can we fit the model or fit the data within this class of functions? Because you can imagine that compared with the linear regression, we have more parameters to estimate. We need to know where is the breakpoint, the change point, and we want to also know what is the best linear regression within each region. So this will be the main topic of my talk. But actually, we can do more fancy things. We can even do a non-parametric estimation. We can fit the data just with a with a constraint shape, such that can we fit the data with a convex function within the whole class of convex functions. So this is a non-parametric statistical estimation problem, and which is called shape regression. But what is good about this class of function is that actually we can transform the shape regression to a parametric estimation problem. It is proved that to fit the data within the family of convex functions actually is equivalent to our previous problem, to a continuous piecewise linear regression problem. And actually, this is the motivation for us to consider the continuous piecewise linear regression. But in operations research, people always talk about planning. In machine learning, people always talk about prediction. So it means that there is a higher level task, a problem solved behind this finite sample training problem. We train the model within some given data, but actually what we want to do is to predict the future value. So which means that actually, but the future data, there are always some randomness behind them. We don't know where is the future data, where is their input, and what about their output. So actually what we really want to do is that we want to take x and y as random variables and minimize the expected loss behind this model's output and the observed output. But definitely, in practice, we never know the probability distribution of the random variable. So what we can actually do is just to approximately solve this population risk minimization problem via the empirical risk minimization. Meaning we can only add to minimize the average loss behind this training or given sample data. And putting all these problems together, this will be the core optimization problems for solving many kinds of data science problems. Okay, optimization has a relatively long history, and there are already very well-developed algorithms and even commercial solvers like Cplex, Gorby to solve optimization problems. So why do we still want to study them? This is because the modern data science problems bring new features and new challenges to the field of optimization and statistics, which they are now extensively studied in the past. So let us re-examine the piecewise linear regression problem, where there is one piece fixed to be 0 and another piece to be linear. But due to this max operation, the objective function is a non-smooth function. And also you can see from the right figure here, this is also a non-convex problem. And consider that our ultimate goal is to solve the population risk or the expected loss behind the model's observed output and the observed output. Actually, the problem is also non-deterministic. But actually, each of these three new features, they are not new to the field of optimization. What makes the problem particularly difficult to solve is the way all these features combine or interact. Even though we ignore the non-deterministic, we consider the finite sample training problem, it is not easy to separate the property of non-smoothness and non-convexity in terms of sum and also in terms of composition. So actually, all these three features, they are inherently combined together in a way we call advanced coupling. So all these non-features motivate us to call this class of problems non-problem, because they all start with none. And I place my role in data science as to solidifying and expanding the foundation via the computation optimization and statistical analysis. So we are trying to design computational methods and conduct statistical analysis to solve these non-problems. So back to my previous slide. From the perspective of optimization, we want to understand what can be computed from the finite sample training problem and how to compute them. And from the perspective of statistics, we are trying to understand what is the asymptotic behavior of the computed solution from the empirical risk minimization. Meaning that, suppose we are given more and more samples coming from the probability distribution of the random variable x and y, then is it possible for the computed solution from this empirical risk minimization converge to a meaningful point of the population risk minimization? But before answering all these questions, let us first try to understand what kind of points can be computed from the non-problems. Because first of all, they are non-convex problems, and in general, we know that it is impossible to compute a global minimizer or even a local minimizer for non-convex problems. What can be computed from numerical algorithm with provable convergence is actually various kinds of stationary points, even when there are non-differentiability. We know that for a smooth function, we call a point stationary point if the gradient at that point vanishes. But for non-smooth functions, the gradient is not well defined at the non-smooth point, the non-differentiable point. But actually, researchers have already generalized the definition or the concept of gradient to the class of non-smooth functions. And the different definition of the generalization of the gradient actually reveals different kinds of stationary points. And these three, as typical three kinds of stationary points considered in optimization. But actually, they are different. For example, we say that in red color, this is a kind of D stationary, and the D is short for directional. We say that this is a kind of good stationary point, in the sense that a point is D stationary point, then it will satisfy all the conditions required by other kinds of stationary points. And it also has more chance to be a local or even global minimizer. So the question is it possible? Or does it deserve the effort to compute a good stationary point? You can imagine that in terms of the computational mathematics, you may need additional efforts in order to compute a good stationary point compared with others. And actually, this is our goal. Our goal is to compute a good stationary point of the empirical risk minimization, or the finite sample training problem. But consider that our ultimate goal is not to solve this problem. Our ultimate goal is to solve the expected loss, the population risk minimization. So a natural question to ask is that, does it deserve the effort? And our answer is yes. Because that we can say that we can prove that actually the sequence of a good stationary point, or we call a shape stationary points, will actually asymptotically converge to a very good stationary point at the population risk minimization, our ultimate goal. Meaning that suppose we are given more and more samples, and in the limit case we are given infinity many samples, then actually the algorithm will converge to a very good stationary point of the population risk minimization. it has more chances to be a local minimizer or a global minimizer. Then it comes to the question, how can we achieve this goal? How can we compute a good stationary point at the empirical risk level? So let's go back to the piecewise linear regression problem. We are given this kind of empirical data, but of course in high-dimensional space. How can we recover? How can we find the best piecewise linear fit of this data?
So in the previous slide, you mentioned the sequence of sharp stationary points converged in stationary populations. Is that a statement or countermeasure?
You mean, is it a rigorous statement?
No, this is clearly not rigorous, but are you saying that you have countermeasure?
Yeah, I will talk about the rigorous statement of this kind of things later.
So it is countermeasure.
Yeah. Thank you. Okay, so let's talk about the optimization problem. How to fit the data within this class of functions. And given the fact that any continuous piecewise linear function, the whole family of this class of functions can be written in this form, the difference of two family of class functions, and within each max, there is a family of linear functions. So the empirical risk minimization is to solve this optimization problem, or we say to estimate the parameters A, alt A, alpha, B, and beta. And actually, this is called an estimate of the change point, like in the linear regression. We don't want to fit the data with only one linear function. We want to know how many, where should this line, the linear regression, change their direction in the high-dimensional space. And actually, our algorithm is a double loop algorithm. Double loop in the sense that there is an outer iteration, which we call the majorization minimization algorithm. And within each iteration, there is another subproblem to solve. And we'll use another numerical algorithm to solve the corresponding subproblem. And actually, we can prove that the majorization minimization algorithm will converge to a good stationary point, a desirable point we pursue for the empirical risk minimization. And the subproblem, the inner problem provided by this majorization minimization algorithm, will be solved by another method called the non-smooth Newton method. And why we use non-smooth Newton method? Smooth Newton method is actually a very classical method in numerical linear algebra to solve the smooth nonlinear equation. But given the fact that we are doing with non-problems, there are non-differentiability in the problems, we cannot use the smooth Newton method to solve the equation. So actually, non-smooth Newton method is a generalization of the smooth Newton method, but for solving non-smooth equations. So here is a bit technical detail. Sorry?
So since you're using a second-order method,
yeah.
you have to compute convention and invert it?
This is a good thing about the non-smooth Newton method. Yeah, definitely, because people always talk about first-order method to avoid this kind of computational cost, possible additional computational cost. And actually, I will talk about why we use this kind of method. Actually, the computational cost for this method is not very high. It is linear in the dimension of the samples. This is the advantage of non-smooth Newton method. That's different from the smooth Newton method. So here is a bit technical detail. The majorization minimization is actually a classical method for solving the non-convex problem. And the idea behind this algorithm is that we are given a surface, and at each iteration point, we are creating a global upper bound of the original objective function, and solve the global minimizer of that upper bound, take it as our next iteration. But when we apply this algorithm to the non-problems with the non-differentiability, the question is, where will this algorithm converge to? So let's see a toy example. This is a one-dimensional problem, and the figure of this function is given here. So suppose the algorithm starts from the 0 point, the red dot here, and we create an upper bound. But what is not good about this upper bound is that the global minimum solution is still this point, meaning that our next iteration is also 0, and the algorithm cannot progress. So it will start at this point, but actually 0 is not a desirable point, in the sense that the directional derivative at this point will not always be non-negative. But this is actually what is required to be a good stationary point. So deep into mathematics, actually this is caused by the non-differentiability of the function at the point 0. So this is the source of difficulty for the non-problems bring to the field of optimization. Then how can we overcome this problem? Is it possible to find a good majorization function such that the algorithm of majorization minimization will converge to a good stationary point, even there are non-differentiability of the problem? So let's re-examine this problem. And actually in the right figure, at this point, we can create another upper bound. But this upper bound is better in the sense that it has a better global optimal solution here. The resulting point will be better than the origin point, and actually this is even a global minimizer of the function. So the problem is, how can we design such kind of desirable upper bound automatically in the numerical computation? And this is what we do. Sorry.
So those points of non-differentiability in higher dimensions is going to be exponential number of dimensions. And not
Exactly.
different,
Yeah.
hyperparabolas you're going to have to fit.
Exactly. Yes. Yeah. This is a difficulty.
So the combinatorial optimization.
Yeah, but actually we will not search among all the possible pieces. We need to define. We need to find a way to design a very good upper bound. And we don't want to search among all the pieces, then that will become a combinatorial optimization problem. Okay, so for simplicity, let us here only take one sample and see how to create a very good upper bound for this kind of functions, such that it will converge to a very good stationary point. So the first step is actually we want to decompose this square function, because this function is not any monotonicity. The figure is given here, but actually this function can be decomposed into the sum of two parts. One part is a convex non-decreasing, and another part is convex non-increasing. So each part there is some monotonicity. Now with this kind of monotonicity, for example, let us consider the first part. Then as long as we can give an upper bound of the inner function, put the monotonicity together, we will have an upper bound of the entire function. And actually it is not hard to give an upper bound because of the inner function, the right part, because we can simply take out the max operation. And actually any piece among the first max operation will be an upper bound of the original function. But definitely, if you can imagine that if we choose all these pieces and we take them as all the candidate upper bound, sum them one by one, it has more chances for our algorithm to converge to a very good stationary point. But yeah, the problem is that it will bring more computational cost because there are many pieces, especially when there are many samples. So actually, we can prove that we don't need to consider so many pieces. We define this is just a mathematical formulation, and we define this kind of index sets. And intuitively, when index belongs to this set, it means that the value at that piece is not far from the max value of among all the pieces. It is actually a critical index set, we see, an important index set for us to consider. And what we are doing in the algorithm is that at each step, we only consider these critical index sets, and we create an upper bound for each index or each piece given among this set. Then we can show that actually the algorithm defined in this way will become a directional stationary point. So this is a way we avoid the combinatorial search, to search among all the pieces. And this is about the formal statement for why we want to pursue a very good stationary point at the empirical risk minimization level. Actually, under some technical conditions, like the moment assumptions on the random variables, we can prove that the directional stationary points, or we say a very sharp kind of stationary points, computed from the empirical risk minimization, will converge to a good stationary point, the same kind of stationary point at the population risk minimization. But actually, what is interesting about this class of problem is that we can do something more. We can analyze the landscape of the piecewise linear regression and see what is the directional stationary point. And what I can actually show is that any directional stationary point of this problem will become a local minimizer in a deterministic sense, no matter how many samples you give. Or in other words, it means that the set of the local minimizer and the set of all the directional stationary points actually coincide. They are the same sign. And we say that under known conditions, just for our piecewise linear regression problem, as long as we use a convex loss function and do this piecewise linear regression, we can prove this property, no matter how many samples we have and how large the dimensional it is. Yeah. So this is a deterministic statement. So actually, it means that any accumulation point computed by our numerical algorithm will be a local minimizer. But we have not finished all our tasks because we create this such kind of global upper bounds, and can we actually solve that kind of upper bound? So this is actually the corresponding subproblem we need to solve from the upper bounds we create for the majorization minimization algorithm. It looks a bit complicated, and it is still a non-smooth problem because of all these max operations. But let me summarize all the key features of this problem. It is an easier problem than our original non-problem in the sense that it is strongly convex, even though it is still non-smooth. And for convex problem, we know that we can always talk about its dual, like in the linear programming. And actually, the dual problem of this one, is a continuously differentiable function. It is a smooth problem. And what is even better is that the gradient of the dual objective function is piecewise linear. So that is to say, to solve the dual problem is actually equivalent to solve a piecewise linear equation, because we can write down its optimality condition. The optimality condition of a smooth unconstrained problem is simply the gradient of that one is 0. So it is equivalent to solve a piecewise linear equation. But how to solve this piecewise linear equation? As I said, we can now use classical Newton method, because classical Newton method is a method to solve smooth nonlinear equation. What we can use is the non-smooth Newton method, a generalization of the Newton method to solve this kind of nonlinear equation. Non-smooth equation. And the convergence rate, just as the classical Newton method, it will converge globally and superlinearly. But definitely with the global convergence, we need to use some line search technique as in the optimization. And this is what I say about the computational cost. Actually, the computational cost of this kind of semi-smooth Newton, non-smooth Newton method is not that high. And here I didn't give many details about the reason. But let us just see more why this kind of things happens. Okay, so this is the main step of the non-smooth Newton method. So here is suppose that what we want to do is to solve this non-smooth equation. And the main step of third is to find a matrix. Actually, this is like the Hessian of the smooth case. But just for non-smooth case, we don't have Hessian. We don't have its gradient of this function. So we need to define a so-called generalized Jacobian. And then this will reduce to a linear equation. And we can use, for the low-dimensional case, we can use direct solver to directly solve this linear equation. And for the very large-scale problem, we can use iterative solver, like the conjugate gradient method, to solve the linear equation. And then this is about the convergence rate. And actually, this is the reason why the computational cost of the semi-smooth, or just we say the non-smooth Newton method, is low. So actually, this is the structure of this previous equation. And why we have this kind of structure? This, I forgot to write down the equation. So this P actually comes from the generalized Jacobian. All these matrices come from the generalized Jacobian. And there is a very particular structure for this kind of generalized Jacobian, always say the Hessian, for solving our piecewise linear regression, because we have some max operation there. And we actually, this kind of matrix, the matrix P here is a diagonal matrix. We only have diagonal elements. All the off-diagonal elements are 0. But the diagonal matrix is only either 0 or 1. And which part is 0? Actually, all the this is theta is the parameter we want to estimate or to solve from this nonlinear equation. And as long as the component of theta, or this as the parameter we want to estimate is 0, then the corresponding diagonal part will be 0. So as long as we want to estimate a very sparse parameter, then actually the computational cost here in total is this order. It needs some numerical linear algebra technique, but this is actually what we do in the numerical computation. The capital N is the number of samples. The value of K1 is the number of pieces, which is usually not large. And number of K2 is also usually not large. They are no more than 10. So putting them all together, the order of this computational cost is almost linear in the number of samples. Okay, so go back to the Okay, so this is an animation of the procedure of our algorithm. And actually, each move means that we solve each iteration of the majorization minimization. We are creating an upper bound for each move. And you can see that within tens of steps, we can actually recover, or we can find the pattern behind this data, a shape M, like the letter M. And these are some further statistics for the computational efficiency of our algorithm. So roughly speaking, for solving a problem with thousands of samples, and we need to use no more than 30 steps of the majorization minimization steps, around 10s or 20s. And actually within each step or each convex problem we need to solve, we roughly need about 10 steps of the Newton iteration, because it is a second-order method with superlinear convergence rate. And roughly the time for solving this large of problem is about 10 seconds, just on my personal computer. And these are some numerical results about our modeling. So whether it deserves effort to consider the piecewise linear structure instead of the linear structure behind the data. And all these numbers in the table, they means the ratio of the prediction error that we compare with the linear regression. So first we train a model with some given samples, with some given data, and we calculate the prediction error or the loss of the observed output, and the value we can compute actually from this model as our prediction error. And when you can see that when K1 and K2 equals to 1, both of them equals to 1, then it means that there are only one piece. So it reduces to the case of linear regression. Now, but if you're given larger value of K1 and K2, you'll have more pieces. It is like an upper bound of the number of pieces you want to estimate. Then compare with linear regression, we want to know whether we can reduce the prediction error, not the training error. Because you can imagine that with more parameters to estimate, you can always reduce the training error for a given data set. But actually, you can see that for this kind of data, when there may be some inherent piecewise structures behind them, actually piecewise linear regression will do a better estimation to find a better pattern behind this data. And actually, our algorithm can do a more general class of problems. Here, L is a loss function. It needs to be convex, but not necessary to be a continuously differentiable function. And actually, we don't need to fix our functional class to be piecewise linear. We can consider, for example, a piecewise polynomial regression. Like we ask the function f and g to be a quadratic function, or even the polynomial function with higher degree. And actually, we can put a regularizer. Here, a regularizer means that we want to find some sparsity behind the data, or some low rankness behind the data. And as long as the function here, P1, is a convex function, so normally, for example, for sparsity regression, people consider the L1 norm to induce some sparsity about the parameter theta. And even we can do something more. We can consider some non-convex surrogate of the L0 norm to consider a better estimation of the sparsity pattern. So putting all this together, this is actually a non-convex regularizer. But our algorithm actually generalize well to solve this kind of problems. Okay, so here comes the last part of my talk about the extension of our approach for solving other problems. And the message here is that actually non-problems are pervasive in data science. So here is a problem to train a deep neural network with feed-forward structure. And we want to consider a particular kind of activation function, where the activation function has two pieces. One part is fixed to be 0, and another part is a linear function. So this is what I said as a building block. The max function is a building block of a very large deep neural network. And actually, for a deep neural network, we throw out the input data into this network. It passes through a linear transformation first. Then we zero out all the negative components, putting them into the second layer, and do similar things until they reach the last layer. So we are trying to know whether we can generalize our algorithm to solve this class of problems with a rigorous treatment. Means that we want to have a rigorous theoretical guarantee to see what kind of points we can compute for this kind of problems. Because you can imagine that it is a highly non-convex and non-differentiable problem. I should say that actually this class of problems is even harder to solve than the previous piecewise linear regression, because we have so many layers nested together. So it is not easy to design an upper bound for this kind of composite structure. And this is actually what we did. We want to overcome the multi-composition of this kind of deep learning problem by just dividing them into the sum of several parts. And actually for this term, it is only coupled by two consecutive layers, because the index L represents a layer. And for this term, it only involves the layer L and L minus 1. And we want to say that this kind of two formulations, they are actually equivalent. And the intuition behind this formulation is that as long as two consecutive layers are connected in a desirable way, then we put all these layers together. The structure of the deep neural network will resolve. So this is a rigorous statement of the equivalence of these two formulations. We prove this statement in the sense of a computable solution, meaning that any directional stationary point, a very good kind of stationary point, we can actually compute it from the numerical algorithm, will be a directional stationary point of the previous problem. So these two problems are equivalent in the sense that what we can actually compute. But for this problem, it is relatively easy to design the upper bound because we don't have so many layers. We don't need to pass through the nested layers to design the upper bound. And actually, this is exactly what we did for the piecewise linear regression. We just used the similar technique to create an upper bound and then solve the corresponding problem by the non-smooth Newton method. And this is the numerical result. We compare with the stochastic gradient descent. where people usually talk about these algorithms for solving the deep neural networks. And we compare it with the one implemented by the Google TensorFlow. And actually, what we find that our algorithm can actually bring down both the training error and the test error to a level that the stochastic gradient descent cannot achieve. And I also want to mention that our algorithm has a rigorous theoretical guarantee for what kind of points we are computing. Rather than the stochastic gradient descent method, when we use it to solve this kind of multi-composite structure, where each of the layer is non-smooth, actually we can now see where this algorithm will converge to. And actually, non-problem also arise from the power systems planning problems. So we imagine that we are in an electricity market where there is a significant proportion of the renewable energy. Then the production from this kind of renewable energy, like the wind and the solar, they are actually random. And also the demand of the electricity is also random. But the thing is that we need to determine the production from the traditional thermal plants before we observe this kind of randomness. And we also need to determine the production from the backup fast ramping generators as a supplement. Then we actually observe the production from this kind of random variable. So in terms of optimization, this is a two-stage stochastic programming. And what is different from the previous energy model is that here, the objective function not only involves the random data, it actually involves the first stage variable. This is because we believe that this is the cost function of the second stage, the production for the from the backup faster ramping generators. And actually we saw that the unit cost of the faster ramping generators actually not only depends on this random data, it also depends on the amount for this kind of second stage production. It depends on the shortfall due to the first stage thermal power decisions. So we imagine that there is a linear dependence for the unit cost and this first stage decision variable. Then we put this first stage decision variable into the objective. But when we put this first stage variable here, this value function, the second stage recurse function, will become a non-convex and non-smooth function. So in other words, this is a non-problem. And it also is a non-deterministic problem because of this kind of randomness. And we can design a rigorous algorithm for solving this kind of problems, which will also converge to a very good stationary point, actually also the directional stationary point. And the non-problems also happens in the individualized decision-making problems. Just as people do in the precision medicine, that they want to estimate the optimal treatment based on the individual background of the patients. And when we incorporate the risk control into this kind of model, actually we find that the corresponding problem will again become a non-problem. And actually this class of problems is even more difficult. The objective function in this kind of optimized individualized decision rule, there is a non-discontinuous function. There is a 0-1 binary function to distinguish different treatment or different outcome of the treatment. But still, we can solve this kind of non-problem by rigorous study from the optimization techniques. So what is usually said in the individualized decision rule is that there is no one-size-fits-all. And actually, I think that this is also quite true for solving non-problems. Every problem has its distinguished structure that we need to take fully advantage when we design numerical algorithms and conduct statistical analysis. So at this stage, together with my postdoc advisor, Dr. Jong-Shi Pang, we are at the stage of summarizing all these source problems and the computational or the statistical tools behind these problems, in order to provide the non-problems a rigorous study for the current and also future applications. So non-problems, what else can we do? Actually, there are more other kinds of non-problems with other kinds of structures. There may not be only a minimized optimization problem. We may have min-max, as in a robust network. We may have infinitely many pieces instead of our only finite piecewise linear regression. Because whenever we consider the low rankness of a matrix, then actually it will involve infinitely many pieces. And it may also be a constraint problem, especially it may involve non-differentiable and non-convex constraint. And it may not be a single stage or two-stage problems, especially in the design of the medical treatment. So we want to pursue the computational methods for all these kind of structures. We are also trying to understand the statistical properties of the computable solution, not the global optimizer. We want to know what kind of statistical inference we can see about the solutions we can actually compute from the numerical optimization. And I'm also trying to expand the applied domains to see where the non-problems can also come. And finally, I want to develop some new software packages for solving the non-problems for the applications from different applied domains. So in summary, non-problems consist of many features that are not faced in the classical continuous optimization. What makes the problem particularly difficult to solve is the way all these features combine or interact. So I believe that instead of just relaxing the assumptions or simplifying the conditions, we need to reach out to the domain experts and understand the real needs behind all these applications to make both the optimization and the statistic fields a non-interbreeding field. So let me end my talk by acknowledging all my collaborators, which consist of a group of optimizers, statisticians, and engineers. But of course, you can now call all of them data scientists. So that's all for my talk, and I'm happy to take any other questions.